Hello friends and welcome. Today I am going to deliver a lecture on calculation of bond energy, bond dissociation energy and resonance energy from thermodynamical data. Now let us first try to have a look at the main objectives of today's deliberation. Number first, to understand the concept of bond energy. Number second, to explain calculation of bond energy. Number third, we shall be explaining the calculation of bond dissociation energy from thermodynamical data, and finally calculating resonance energy from thermodynamical data. Now, we will start with the introduction about the concept of bond energy. The bond energy is a measure of the amount of energy needed to break apart 1 mole of covalently bonded gases. In chemistry, bond energy designated as capital E or bond enthalpy designated as capital H is the measure of bond strength in a chemical bond. IUPAC defines bond energy as the average value of the gas phase bond dissociation energies for all bonds of the same type within the same chemical species. For example, the carbon-hydrogen bond energy in methane is the enthalpy change involved with breaking up one molecule of methane into a carbon atom and 4 hydrogen radicals divided by 4. Tabulated bond energies are generally values of bond energies averaged over a number of selected typical chemical species containing that type of bond. Bond energy or bond enthalpy should not be confused with bond dissociation energy. Bond dissociation energy is the average of all the bond dissociation energies in a molecule and will show a different value for a given bond that the bond dissociation energy would. This is because the energy required to break a single bond in a specific molecule differs for each bond in that molecule. For example, methane has 4 CH bonds and the bond dissociation energies are 435 kilojoules per mole for CH3H, 444 kilojoules per mole for CH2H, 444 kilojoules per mole for CHH and 339 kilojoules per mole for CH bond. Their average and hence the bond energy is 414 kilojoules per mole, even though not a single bond required specifically 444 kilojoules per mole to be broken. When more bond energies of the bond in different molecules that are taken into consideration, the average will be more accurate. Keeping in mind that average bond values are not as accurate as a molecule specific bond dissociation energies. Double bonds are higher energy bonds in comparison to a single bond, but not necessarily two-fold higher. Triple bonds are even higher energy bonds than double and single bonds, but not necessarily three-fold higher. Atoms bond together to form compounds because in doing so they attain lower energies than they possess as individual atoms. A quantity of energy equal to the difference between the energies of the bonded atoms and the energies of the separated atoms is released usually as heat. That is, the bonded atoms have a lower energy than the individual atoms do. When atoms combine to make a compound, energy is always given off and the compound has a lower overall energy. When a chemical reaction occurs, molecular bonds are broken and other bonds are formed to make different molecules. For example, the bonds of two water molecules are broken to form hydrogen and oxygen, given as twice H2O gives twice H2 plus O2. Bonds do not break and form spontaneously and energy change is required. The energy input required to break a bond is known as bond energy. While the concept may seem simple, bond energy serves a very important purpose in describing the structure and characteristics of a molecule. It can be used to determine which Lewis dot structure is most suitable when there are multiple Lewis dot structures. When a chemical reaction occurs, the atoms in the reactants rearrange their chemical bonds to make products. The new arrangement of bonds does not have the same total energy as the bonds in the reactants. Therefore, when chemical reactions occur, there will always be an accompanying energy change. In some reactions, the energy of the products is lower than the energy of the reactants. Thus, in the course of the reaction, the substances lose energy to the surrounding environment. Such reactions are exothermic and can be represented by an energy level diagram like the one shown here. In most cases, the energy is given off as heat, although a few reactions give off energy as light. In chemical reactions where the products have a higher energy than the reactants must absorb energy from their environment to react. These reactions are endothermic and can be represented by an energy level diagram like the one shown here. Exothermic and endothermic reactions can be thought of as having energy as either a product of the reaction or a reactant. Exothermic reactions give off energy, so energy is a product, while as endothermic reactions require energy, so energy is a reactant. Now, let us take some examples. Example first, is each chemical reaction exothermic or endothermic? Number first is twice H2 plus O2 gives twice H2O plus 135 kilocalories. And number second is N2 plus O2 plus 45 kilocalories gives twice NO. Now, the solution for this example is, because energy is a product, energy is given off by the reaction. Therefore, this reaction is exothermic. This is for the first reaction. And for the second reaction, because energy is a reactant, energy is absorbed by the reaction. Therefore, this reaction is endothermic. Now, let us discuss the example second. What is the enthalpy change for this reaction and is it endothermic or exothermic? The reaction is H2 plus I2 gives twice Hi. Now, the solution for this example is, first look at the equation and determine what bonds exist. The bonds exist as one HH bond, one II bond and two HI bonds. Then examine the bond breakage which is located in the reactant side. That is, 1 mole of HH bonds gives 436 kilojoules per mole and 1 mole of II bonds gives 151 kilojoules per mole. Therefore, the sum of enthalpies on the reactant side is 436 kilojoules per mole plus 151 kilojoules per mole, which comes out to be 587 kilojoules per mole. This is how much energy is needed to break the bonds on the reactant side. Then we will look at the bond formation which is on the product side. That is, 2 moles of HI bonds gives 297 kilojoules per mole. That is, the sum of enthalpies on the product side is twice multiplied by 297 kilojoules per mole, which is equal to 594 kilojoules per mole. This is how much energy is needed to break the bonds on the product side. The net change of the reaction is therefore 594 minus 587, which is equal to plus 7 kilojoules per mole. Since this is positive, that is delta H is greater than 0, the reaction is exothermic. Hess's law relates to this equation as it depicts how the energy of the overall reaction is equal to the sum of the individual steps involving energy change. Now, let us discuss the next part of our today's lecture, that is spontaneous and non-spontaneous reactions. A spontaneous reaction is a reaction that, once begun, takes place without outside assistance. An example is a reaction between hydrogen and oxygen. Once the mixture is ignited, the reaction to form water continues until all of one reactant is consumed. The reverse reaction, that is decomposition of water to hydrogen and oxygen, is non-spontaneous. This reaction will occur when an electric current is passed through aqueous solution containing an electrolyte such as NaOH. Thus, decomposition continues as long as the electric current is supplied. Predicting whether a given reaction will occur spontaneously or not under a given set of conditions is important for chemists. The reaction between hydrogen and oxygen and many other spontaneous reactions are exothermic. So, we can assume that one of the driving forces that determine whether a reaction is spontaneous is a tendency to give off energy. However, there are also rare endothermic spontaneous reactions. Dinitrogen tetroxide decomposes spontaneously at room temperature. That is, N2O4 gives twice NO2, in which delta H is equal to 57.2 kilojoules per mole. Now, coming to the application of bond energies. Number first is the determination of enthalpies of reactions. Number second, determination of enthalpies of formation of compounds. Number third, and determination of resonance energy. Now, let us discuss bond dissociation energy. A chemical bond can be defined as the interaction force between two bonded atoms in a molecule. The valence electrons of bonded atoms are involved in bonding. We know that all atoms tend to get the octet configuration for stability. Therefore, they can either involve in ionic bonding or covalent bonding to get this octet configuration in their valence shell. For ionic bond, this is also known as electrovalent bond. One of the atoms loses electrons and form cation, which carries a positive charge, whereas other atom gains electrons to form anion, which carries a negative charge. The positively charged atom or cation and anion are attracted towards each other by electrostatic force of attraction that is known as ionic bond. On the contrary, covalent bond involves the equal sharing of electrons between two atoms and forms a chemical bond between them. The formation of chemical bond requires some energy, which is called as bond formation energy. In other words, the same amount of energy is required to cleave the bond. The energy of the bond also determines the strength and stability of it. A strong chemical bond forms more stable molecule, whereas a weak interaction between atoms forms an unstable molecule. Hence, we have to determine the strength of chemical bonds so that we can predict the stability of the molecule. The bond dissociation energy helps us to determine the strength of chemical bonds. In chemistry, bond dissociation energy is one measure of the strength in a chemical bond. It can be defined as a standard enthalpy change when a bond is cleaved by homolysis with reactants and products of the homolysis reaction at 0 Kelvin, that is absolute 0. For instance, the bond dissociation energy for one of the CH bonds in ethane is defined by the process. CH3CH2H gives CH3CH2 plus H. Here DO is equal to delta H is equal to 101.1 kilocalories per mole is equal to 423.0 kilojoules per mole is equal to 4.40 eV per bond. The bond dissociation energy is sometimes also called the bond dissociation enthalpy or bond enthalpy, but these terms may not be strictly equivalent, as the latter usually refers to the above reaction enthalpy at 298 Kelvin, that is standard conditions, rather than at 0 Kelvin, and differs from DO by about 1.5 kilocalories per mole, that is 6 kilojoules per mole in the case of a bond to hydrogen in a large organic molecule. Nevertheless, the term bond dissociation energy and the symbol DO has often been used for the reaction enthalpy at 298 Kelvin as well. Except in the case of diatomic molecules, the bond dissociation energy is different from the bond energy, which is an average calculated from the sum of the bond dissociation energies of all bonds in a molecule. For example, an HOH bond of a water molecule has 493.4 kilojoules per mole of bond dissociation energy, and 424.4 kilojoules per mole is needed to cleave the remaining OH bond. The bond energy of the covalent OH bonds in water is 458.9 kilojoules per mole, which is the average of the values. Hydrogen bond dissociation energy in water is about 23 kilojoules per mole. Evaluation of bond dissociation energy is a typical application of thermochemical information. The information on bond dissociation energy may indicate which bond is more likely to break in a molecule and can be used to estimate the temperature range. The reaction of bond dissociation can be written as follows: AB gives A plus B. For the above equation, the differences between enthalpy and energy can be written as delta H minus delta E is equal to summation of PV fragments minus PV molecules is equal to delta nRT. There is a variation in bond energy and bond enthalpy, that is, true bond energy should be taken at 0 Kelvin and not at 298.3 Kelvin. However, these differences are very small compared to the value of the bond dissociation energy, and in general the bond dissociation energy is taken as equal to negative value for the enthalpy of formation of the bond. The enthalpy of bond dissociation is given by the expression delta H0 F A minus B is equal to delta H0 F A0 plus delta H0 F B0 minus delta H0 F A into B. Now, let us discuss the last part of our today's lecture, that is resonance energy. In chemistry, resonance or mesomerism is a way of describing delocalized electrons within certain molecules or polyatomic ions where the bonding cannot be expressed by one single Lewis structure. A molecule or ion with such delocalized electrons is represented by several contributing structures, also called resonance structures or canonical structures. Each contributing structure can be represented by a Lewis structure with only an integer number of covalent bonds between each pair of atoms within the structure. Several Lewis structures are used collectively to describe the actual molecular structure, which is an approximate intermediate between the canonical forms called a resonance hybrid. Contributing structures differ only in the position of electrons and not in the position of nuclei. Electron delocalization lowers the potential energy of the substance and thus makes it more stable than any of the contributing structures. The difference between the potential energy of the actual structure and that of the contributing structure with the lowest potential energy is called the resonance energy or delocalization energy. Resonance is distinguished from isomerism. An isomer is a molecule with the same chemical formula, but with different arrangement of atoms in space. Resonance contributors of a molecule, on the contrary, can only differ by the arrangements of electrons. Therefore, the resonance hybrid cannot be represented by a combination of isomers. In other words, the resonance energy of a compound is a measure of the extra stability of the conjugated system compared to the corresponding number of isolated double bonds. This can be calculated from experimental measurements. A compound with delocalized electrons is more stable than it would be if all of its electrons were localized. The extra stability a compound gains from having delocalized electrons is called delocalization energy or resonance energy. Electron delocalization gives a compound resonance. So, saying that a compound is stabilized by electron delocalization is the same as saying that it is stabilized by resonance. Since the resonance energy tells us how much more stable a compound is as a result of having delocalized electrons, it is frequently called resonance stabilization. To understand the concept of resonance energy better, let us take a look at the resonance energy of benzene. In other words, let us see how much more stable benzene with 3 pairs of delocalized pi electrons is than the unknown, unreal hypothetical compound cyclohexatriene with 3 pairs of localized pi electrons. The delta H0 for the hydrogenation of cyclohexene, a compound with one localized double bond, has been determined experimentally to be minus 28.6 kilocalories per mole. We would then expect the delta H0 for the hydrogenation of cyclohexatriene, a hypothetical compound with 3 localized double bonds, to be 3 times that of cyclohexene, that is 3 multiplied by minus 28.6, which is equal to minus 85.8 kilocalories per mole. That is all about today's lecture. Hope you have understood it very well. Thank you very much and goodbye.